conservation laws. And so we'll do the conservation of mass, or the continuity equation, which we looked at already when we defined the stream function. And so we'll derive the conservation of mass in differential form and in integral form. Then we'll see what the continuity equation looks like. And then we'll see one or two applications. Then we'll see the conservation for a substance. Okay, so instead of mass, we're going to look at conservation of a substance. So for example, if in atmospheric dynamics you want to look at the concentration of ozone or whatever traces in the atmosphere, in the ocean, or in any fluid, for example, then we'll reduce the equation, under certain condition we'll reduce the equation, the conservation, into the advection diffusion equation, which I believe you have used in numerical methods, probably, or maybe you'll do it in numerical methods too. You will write down a code for the advection diffusion equation. Okay, so today you will see where it comes from. And under certain condition, the advection diffusion equation reduces to the diffusion equation. Okay. So that will be the class for today. And then we'll do the conservation of momentum. Okay. So we'll start from first principles. So we'll derive the Cauchy equation. Then we'll derive what are the Navier-Stokes equation for Newtonian fluids. Okay, so those are the equations that you will use all the time in atmosphere, ocean, or solid earth, and Navier-Stokes equations. And the Navier-Stokes equation we'll briefly introduce rotation. Okay, so you will see that there's an extra term in the Navier-Stokes equation that is due to the rotation of the Earth. And so in that case, it will not be fluid dynamics, but geophysical fluid dynamics. Right? But you will see that properly in the second part of the course. And then we'll reduce the Navier-Stokes equation to the Euler equation, okay? And then the case for a rotating frame, just to give a little bit of an introduction of what will be the equation in a rotating frame in the second part of the course in GFD. So in GFD, in the second part of the course, we will start with the Navier-Stokes equation with an extra term due to rotation, and next time is when you will see from first principles how to get there. Okay. And then we'll do the conservation of energy. So kinetic energy, mechanical energy, potential energy, and total energy. And just a very brief I think we'll do it first and second law of thermodynamics, okay? With the conservation of energy. And then a nice application of the conservation of energy, which is the Bernoulli equation, or the Bernoulli principle, okay? Which is something that is used and is quite common in many applications of fluid dynamics. Okay, if you have any questions about previous lectures, no? Should I go on, or do you want to, well, maybe we'll do it at the end of the class, you know, just stop me anytime during the class, before the class, or after the class, saying, you know, can you please redo whatever you did the last time, or whatever you're doing now, okay? Because it's better to talk about things while you're doing it, instead of 2 months ago you said this. It's better for you and for me, so when it's fresh in our mind. Huh? I think so, yes. But before we start doing the conservation laws, so today the conservation of mass, I'll show you what the Leibniz theorem is, which is something that we will use and is quite useful. Okay. Which is a way of integrating over a volume. So we'll start looking at the conservation laws, mass, energy, momentum, and so forth, and we're going to do it, as I said, in differential form and in integral form. And we're going to do this over a certain region or over a certain volume. Okay, so we look at an infinitesimal volume of fluid, and we're going to do the conservation of mass in that volume of fluid, or the conservation of momentum, or the conservation of energy. Okay. Now, the volume that we take, it might be a volume fixed in space. Okay, so we take a certain volume of fluid, like for example this room, it's fixed in space, and we look at the conservation of mass within this room. Okay, so the volume over which we integrate mass is fixed in space and in time. Or it could be what is called a material volume. Okay. And in this case, the material volume moves with the flow. Okay, so moves with the fluid. So for example, in a Lagrangian way, you're following the fluid, okay, and you take, for example, in the ocean, you want to look at a water mass, okay, that we will define in physics and dynamics of the ocean. So a water mass is a volume of water that has that conserves its property for a long time. Okay, so temperature, salinity, or for example oxygen. Okay, so that mass, that ocean mass, water mass, travels and is affected by the ocean circulation. Okay, and you can track that water mass. Okay, there are many water masses. For example, North Atlantic deep water, Antarctic bottom water. Okay, there's many different water masses that are characterized by a certain temperature, salinity, or oxygen. Okay, and so, for example, if you're following that water mass is moving. Okay, and you want to do the conservation of mass, or the conservation of momentum, or the conservation of energy of that water mass. But that water mass moves, so that volume over which you integrate is moving. Okay, is moving with the flow. And a third case is a volume that is neither fixed in space and is not moving with the fluid. So it's moving at a different speed. Okay? So I don't know, there's a flow going in a certain direction at a certain speed, and I take my volume of integration and I move it differently. Okay? Just because I want to, just to, in order to generalize things. Okay. So third case, none of the above. Okay. So when you do the volume integral, you have to be careful if you are in which case you are, and I'll show you why. Okay, so we want to find the time. So again, we always look at rate of change. Okay, so we look at time derivatives. So we're going to look at the time derivative, the d by dt, and we integrate our function over a certain volume. Right? So we want to integrate over a certain volume, for example, mass, and look at the conservation of mass, and we look at the rate of change of this. So this volume over which we integrate, it might change in time. Okay, so it might be the second case or the third case. So the volume over which we integrate, it might be moving in time. So f is a tensor, okay, and v is our volume over which we integrate, which in this case is changing in time. So we want to perform this time derivative of an integral over a volume integral. Okay, so we're going to take a general case. So the last case, okay, the volume over which we integrate is moving, but it's not moving at the same speed as the fluid. So it's not a fixed volume and it's not a material volume. So I hope this helps. We're going to do, instead of looking at volume, we're going to do a one-dimensional case first. Okay, so we have our function f, which is this one, and the limit of integrations are a1 and, for example, b1. Okay, and we integrate this function, this tensor, between a1 and b1. But then instead of a volume that is moving in time, in this case we have a line that is moving in time. Okay? So at time, so this would be the integral of f over dx at time t. But then we might have f of xt plus dt, and this is going to be my integral of f over dx at time t plus dt. Okay, so the region over which I'm integrating has changed over time, and now the limit of integration I have also changed. So now we have f2 and we have b2. Okay, so the limit of integration have changed because in this case our volume is a line segment, and that has changed in time. So this is going to be the change in time after some dt of f dx. Okay. F has changed in time, and I integrate that in space. In this case, it's not a volume. Okay. But then we have this. We have a change in the limit of integration dA and dB. Okay, those limit of integration have also changed, and they are dA f of a t, and this is dB f of bt. Okay. So this is a moving rate, and the rate is dA, in this case is dB. So the moving rate will be dA over dt, and the rate will be dB over dt. Okay. So in this case is a rate of loss, and in this case we are gaining. Okay. So here we are losing f, and here we are gaining some f. Okay. So the initial limit of integration was a1, now is a2, so we have lost this. And the initial limit of integration was b1, and now it's b2, so we have gained some dB in that case. Yes?
Why do you multiply the change in the limit by the force?
Force? No, f is a tensor, is whatever. I mean, it could be density. So later we will generalize to density for the conservation of mass. So it's not just the change in space of f, but it's also the change in space with the rate of change of the limit of integrations. Okay? So the rule of differentiating this integral becomes something like this. My d by dt, so my rate of change of f, which is a function only of x in this case, x and t, sorry, dx, and the limits of integration are a, which is a function of time, and b, which is a function of time. Okay, so I want to integrate that function f, which is a function of space and time, and I'm looking at the rate of change of f. So this is going to be my integral of the change in time of f in x. So that will be this integral over here, okay? Plus the fact that the limit of integration have moved. Okay, so you have to take into account that you lose something here and you gain something here. And that is given by the rate of change dB by dt, and I put a plus because in this case is I'm gaining my f at b minus AD by dt of f at A. Okay? So the limit of integration at A, I am losing at a rate of dA by dt. And I'm gaining at the limit of integration B at some rate dB by dt.
So what is that expression? dA times FA.
This would be the how f changes at A in time and changes some dA. Okay? And f at B, it changes some dB. So the rate of change, so d by dt of A, and the rate of change here is d by dt of B. Okay? So the limit of integration at A and the limit of integration at B, they move some dA and some dB. Okay? Which is this dA and this dB. This could be 0, we'll see. Okay, so if the volume was a volume fixed in space, the limit of integration would not move. So the rate of change of the limit of integration would be 0. Okay, this dA would be 0, this dB would be 0, and these two terms would be 0. Is that clear?
Please, can you kindly explain how the dB is gaining and then the A is losing? I don't get that concept.
So I used to have this integral from A to B, okay? Now I'm integrating from A at time 2 and B at time 2, okay? So before I was integrating from here to here. Now I'm integrating from here, so I lost this space, and I'm integrating more in X. So in this case, here I'm gaining, and here I'm losing some of the integration. So this is the integral of the change of f in time, okay, over the region. So how f changes in time integrated over the region. In this case is one-dimensional, so it's x. So you want to look at the conservation of mass, for example. So how does mass changes in time integrated over some space? This would be how this f changes in time integrated over this line in x. Okay. And this are the outer and inner boundary that are moving. So they're giving you a gain in one case and a loss in another case of your tensor f, or density. Because the limit of integration are moving, they're in the boundary giving gain loss what? At a rate dV by dt, dA by dt. Okay. So if you want to look at the time derivative of this integral, there are three terms here. So there's the change in f, so the time derivative of f integrated over the volume or space. Okay, so that the integral of the variations in f over the region that you're interested in, over which you're integrating. But then you have to take into account, because you integrate over some region that is moving in time, so you have to take into account the fact that the limits of integration are changing. Okay? So you're not looking at the time derivative of f here at t and then the change of f integrated over the same region. But the region is actually changing. Okay? So you have to do the change in time of f integrated over the space plus the fact that the limits of integration are moving. Okay? So you're not integrated over the same space. And the way these limits of integration are changing, they are given by a rate of change of those limits of integration. They are dv by dt and dA by dt. Okay? So we can generalize this not in a 1D but a 3-dimensional volume. So we can write that the time derivative of some f, function of space and time, integrated over a volume that is changing in time. So in this case, there was a line changing in time. Now it's a volume over which we are integrating that is changing in time. So we want to look at the rate of change of that function f integrated over a volume. That is going to be the volume integral over the volume of the rate of change of your function plus, now we're not integrated over two limits of integration, but it's a volume, so the limit of integration is going to be the area bound in the volume. So we are integrating over an area that is a function of time, of f, times u, so the rate of change, this will be the velocity at which the limits of integration are changing, some dA. Okay, so we went from a one-dimensional case where the limits of integration were changing in one dimension. Now we are integrating over a volume. So the rate of change of this function integrated over a volume is going to be the change of f in time integrated over a volume, but then the volume is moving. And what is the limit of integration of the volume? That's the surface or the area bound in the volume, right? It's not A and B anymore. And that is given by f, okay, times the velocity at which the area is changing. That will be my u dA. Okay. So here there are going to be gaining and losses given by the fact that the area bound in the volume is moving. Okay. That's my limit of integration over my volume. Okay, and this is called the Lydon Theorem. So you cannot just say that the time derivative of a volume integral is equal to the volume integral of the time derivative of the function. You have to take into account the fact that maybe the volume over which you are integrating is moving. So the limits over which you are integrating is moving. And is moving at a certain speed. In this case, the rate of change was dA by dt and dV by dt. That was the speed at which it was moving. Okay. Now it's some velocity over which the area over which you are integrating is moving. Okay. So you have to take into account also the fact that the volume over which you're integrating is moving. It's not just the derivative in time of f integrated over a volume. If the volume is not moving, this term is equal to 0. Okay. If the volume over which you're integrating is not moving, the velocity at which the limits of integration are moving is equal to 0. And so the time derivative of the volume integral is equal to the volume of the time derivative of f. Okay. So the volume is fixed, this room is fixed. How does density changes in this room, integrated or in this room? Well, it's just the change in density integrated in the room. Okay? But if the room is moving, then it's the change in density in time integrated over the room, and the fact that the room is moving at some velocity u. Okay? Because the limits of integration of this volume is moving in space. Okay? So in the general case, we were in the general case, no, were we in the general case? Yes, okay. So now we can make the approximations for this case and this case, which are pretty obvious. So for a material volume, so this will be general. Okay. For a material volume, you want to look at the change in time of your function or your tensor f integrated over some volume, and that is going to be the change of f integrated over the volume plus the fact that the area bounding the volume is moving, so you have to integrate that over the surface area. And in this case, the velocity of the volume over which you're integrating is equal to, in a material volume, is equal to, in a volume fixed in space, the volume doesn't change. In a material volume, the room is moving with the fluid. Mm-hmm. So U is equal to U of the fluid. Okay, so the fluid has some velocity, there's a flow, and you are following that water mass, for example, okay, that is a vector at a certain velocity because the fluid flow has some velocity UF, so you are following that water mass. And so the velocity at which the volume over which you're integrating is the velocity of the fluid. Okay, there's a wind blowing on this room, and this room is moved by the wind. Okay, so the velocity at which the room moves is the velocity of the wind.
Is that not the relative velocity? Is that not the relative velocity? For example, if that's the relative velocity of the room with respect to the fluid, then it will be zero.
No, but you're integrating over that volume, okay? And the volume is moving at some speed. You're not in the fluid, so for you the velocity will be zero, but you're not in the fluid. Okay. So you're looking at some volume, and that volume is not fixed in space because it's moving. So you're trying to integrate something, density, for example, over that volume, but that volume is moving at a certain speed. In a material volume, is moving at the same speed as the flow. So you have to integrate that volume, and so the changing time of density is going to be the integral over that volume plus the fact that the surface bounding the volume is moving at a certain velocity, which is the velocity of the fluid. So you have to integrate your density over the area bounding the volume that has a velocity equal to the fluid. And in a fixed volume, what is the time derivative of the volume integral of f in a fixed volume?
First time?
Just the first time. And v is not a function of time anymore. Okay. So this is the most common case. Okay. We integrate the volume, F over this room, and the room is not moving.
So, if we have the condition like the fluid is moving and suppose the object is not moving, then what will be the velocity? What would be the form of the expression of the last term?
The object is not moving, so it's a fixed volume. So we are integrating, we'll do it in a second. We are integrating density in this room, okay? And there's some influx of density on one side and outflux of density on the other side. But the volume is not changing. The volume is not moving, right? So what is the change in density in this room? So if I open the window here and I open a window on the other side, what is the change of density in this room? Okay, it's just this term. Is the change of density in time integrated over the room.
Oh, so it's like we are inside that room. We are not looking from outside the room. We are within the frame of the reference.
No, we don't have to.
We don't have to.
I'm outside and I want to compute the change in density in this room. The volume over which I am integrating is fixed, is this walls. Okay? And there's a window open here and a window open there. So there's some density in and some density out. So how does density changes in this room? Is the change in time of density integrated over the room. Nothing else. But if the room is moving, then I have to take into account that the room is moving. And I have to do the change of density in time integrated over the room, but the room is also moving at some speed. And I have to integrate that. Otherwise I cannot integrate over the same limits because the limits are changing, the limits of integration. Like in this case, if this was a volume, the volume is moving, so I'm not integrating between A1 and B1 anymore. After some dt, I'm integrating between A2 and B2. And for a volume, I'm integrating, the limits of integration are the area bound in the volume. So those are the limits of integration. They are changing in time. And actually perhaps you actually should know this. Okay. This case, the material volume, which is the most common, okay, usually either you use a fixed volume or you use a material volume, so you're following a volume that is affected by the flow, or the volume is fixed, like in this room, okay, you don't change that. In this case, in the material volume, is called Reynolds transport theory. Okay, this is quite common in physics. Okay, so if the volume of which you're integrating is moving and is affected by a fluid at the same speed, that's called the Reynolds transport theory. And you integrate the rate of change of your function f over the volume that is moving with the fluid. Okay, so if you take a stream tube, for example, okay, and you give some limits on the stream tubes, and you follow that fluid as it moves in the stream tube, okay, for example, you're integrating the rate of change of density within that stream tube, then the stream tube is moving, that volume that you choose, okay, and it's moving at the same speed as the fluid. So the change in density will be given by the changes in density over that volume and the fact that the volume is moving. So the limits over which you are integrating are changing. This dA by dt and dV by dt don't have to be the same. Okay? So now we can start with the conservation of mass. And we're going to do it for an infinitesimal volume of fluid, and it's going to be a fixed volume, to make it simple. Okay? So we're going to do the conservation of mass for an infinitesimal volume of fluid that is fixed. So we don't have to take into account the fact that the limits of integration are changing in time. Okay? So that my d by dt of the change in density are going to be simply this, okay, to make it simple. So we're going to look at changes in mass, not simply density, so we're going to look at changes in mass per unit time. This. So I have this surface A on this side of the volume and this surface B on the other side of the volume. Okay? And this volume over which I'm integrating is not moving, it's fixed in time. So the changes in my mass integrated of the volume are just the changes in mass integrated of the volume. Okay, so we're going to look at mass. So rho times v, so rho dx dy dz. So just looking at one side, we have some mass in, so this is dx, this is dz. So I have some rho dx dz advected at some velocity. This is should be u. I don't know why I do. Well, let's say v. So this is x2, x1. X3. Okay. So I have some mass in and I have some mass out. It's going to be rho dx dz advected at some velocity. Okay? So just obviously in this sense as well, some mass in, some mass out, some mass in and some mass out. Okay. So we do again, like we did the last time, some Taylor expansion on this. Okay. So my f of x plus dx. In a way I changed notation, but so dx. Okay, and you can do that in the three x directions.
So the density is changing, yeah, with respect to the volume.
I have some mass in and some mass out.
Mass in and mass out.
Okay, and I have to do the conservation of mass within the volume of integration. Okay, so I'm looking at the mass. Rho. This is v volume and this is v velocity. Okay. So I have some mass in and some mass out. So for example, the wind is bringing me some mass in, and then the window open over there is going to be some mass
No
out.
sink and no source inside the volume.
Hmm?
No any sink, no source inside the volume. So that whatever, how many the mass.
Inside nothing is happening. There's just mass in and then mass out of the volume. There's no creation of mass within the volume. Okay, so at B, I have rho dx dz times velocity v is equal to rho dx dz velocity v plus some dy, so this is dy of rho dx dz v dy. Okay, whatever has happened. It could be more, it could be less. And you can do this for all the directions, of course. Okay, in the x1 direction and in the x3 direction. Okay. So the outflow of density at B on this side.
Sorry, is it B column or B multiplying that?
Sorry. At B.
Okay.
Okay. You have the advection of mass is equal to whatever was in plus whatever has changed in this delta y. Okay? And you can do this for all the different directions. Okay? So the rate of change of mass within the volume, yes?
Say mass in, mass out. Do you mean that you are integrating mass with respect to time and space?
Not yet. So we'll do the volume integral. Okay, so there might be some mass coming in from this window, okay, and some mass is getting out from that window. They don't have to be equal.
So it's the within the space you are moving and with respect to time.
And which time? Yes, so we're doing this. So what is the rate of change of my mass integrated over the volume? So we have to integrate over the volume and see what is the change in mass within the volume.
Sorry, saying mass in, mass out, you're multiplying with V. Is the problem?
V is the velocity, sorry.
Okay.
So, I don't know, put okay, you have some velocity V, and in this case you had some velocity U, so here you would have rho dy dz vectored by some velocity u in this direction, and here you would have some rho dx dy vectored by some velocity w.
Rho x dy is m for n is like the mass.
Yes, because we're not looking just at density, we're looking at volume, mass. Sorry. Okay, so that will be rho times volume.
Okay. The x dy is like.
How much density is getting into this area,
Okay.
the x dy,
Okay.
advected by some velocity. Okay. And through this area A, there is some density advected by some velocity v, dx dz.
Okay.
So the rate of change of my density, so I'm looking at the rate of change of mass, sorry, dx dy dz. Okay, so this is actually what I want to know. What is the rate of change of my mass integrated over the volume? This is going to be, so if you do the mass at B minus the mass at A, it will be this minus this, so we're just left with rho dx dz dy dz dy dz. What did we call it? We call it u dx minus e by dy of y dx dz, and we call it v y minus e by z of rho dx dy w dz. Okay, so if you do mass out minus mass in, so at B minus A, you're just left with minus change in y of your mass, so this term. If you do it in the x direction, you get this, and if you do it in the z direction, you just left with that. Okay, so that will be the rate of change of my mass within the volume. Yes?
I'm a bit confused. You started with the time derivative, then you ended up with the spatial derivative. How is that?
Well, what is the change? What is the rate of change of density within this volume? Is whatever comes in and goes out in the x direction, plus whatever comes in and out in the y direction, plus whatever comes in and out in the z direction. So I integrate, eventually integrate, it's like doing an integration in the volume. In the x direction, in the y direction, in the z. If I change density in the x, in the y, and the z, that will give the total rate of change of my mass. So I lose mass in the x direction, for example, so there is a rate of change in mass in the x direction and not in the y and z direction.
Why the minus? Sorry, I'm lost.
Why is minus? Okay. You have some flux in and some flux out.
Okay.
Okay. So what is the rate of change in the x2 direction? Is whatever goes out at B, whatever goes out at, so in minus out. Okay. So I get an influx and an outflux.
Okay.
Okay. So what comes in is rho dx dz v. This is what comes in.
Yes.
What goes out is this, rho dx dz v plus whatever happens in the y direction, rho dx dz v dy. Okay. So it's not equal. So is in minus out.
Okay.
Okay. Okay. So this goes with this.
Okay.
Okay.
This is, do you know what is coming out?
So influx minus outflux is given by this. Perhaps there's no change in the y direction, so 100% comes in and 100% comes out in this direction. So the change in the y direction is equal to 0. So this is 0. So in minus out in this direction, in minus out in the direction. So I have an influx of mass and an outflux of mass. I have an influx of mass and an outflux of mass. You can change the direction of the flow, it doesn't matter. So eventually the rate of change of my mass in the volume is given by the changes in the three directions. So I get rid of this. Okay. And so you can write this .
Density could have also gone, just as you cancel the other in the volume.
So it's not dependent on the volume. Okay. So how does the mass changes over this volume of integration? It's just given by the changes. The volume of integration is always the same. So it's given by the changes in density in time, plus whatever is advected by the flow in and out in all the different directions. And this is the continuity equation. So now imagine you have a steady flow. So d by dt is equal to 0. Okay, there's always the same mass because the flow is steady. So d by dt is equal to 0, so you're left with less, right? If the flow is steady.
Sir, steady or incompressible? Because density
Incompressible is going to be,
density constant, so it would be
yeah, it's going to be the next step. For an incompressible flow, the continuity equation takes a different form. Okay, so time derivatives are equal to 0, so d by dt is equal to 0. So the continuity equation reduces to this. So for example, you can take a string tube.
If density is not changing with time, it's constant.
Imagine that's a string tube.
You went from continuity equation for a steady flow, and then you said the change of density is 0.
Changes in time. So the d by dt is equal to 0. So the flow is steady.
So, okay, sorry, again. If the rho dt is equals to 0, the flow is steady.
It's steady. It's not, I'm not saying that u is equal to 0. Okay?
But it's possible that the rho dt is not equals to 0. When it's not equals to 0, the flow is not steady. Is that what it means?
Repeat that.
If the rho dt is 0, you say the flow is steady. Is it possible that the rho dt might not be equals to 0, but equals to something else, like the density and it vary with time?
Well, no, I mean, so, okay, so if you change pressure, density changes, yes, but we're not considering that.
Okay.
So for a steady flow, you can reduce the continuity equation to this, and we'll see for an incompressible fluid what happens.
But I thought that's the definition of an incompressible or incompressible fluid is when the density doesn't change.
We'll do the incompressible fluid in a second, okay? So we'll see the difference. Are we going to do it? For an incompressible fluid, the density doesn't change in space and time. Okay? So he was just saying that the flow is steady, so the changes in density in time are equal to 0. It's different from the incompressible condition. Well, just give me 10 minutes, okay? And we'll do the incompressible case. Okay? So you can take a string tube, for example. Okay, these are all the streamlines, and there's an area A1 here, and there's an area A2 here. Okay? So we have an inflow, and we have an outflow. Okay? The inflow will be ρ1 U1, and the outflow will be ρ2 U2. Okay? So the flow is steady, so we are in this condition. So we have ρ1 U1 A1. Okay, we were looking at the side A and the side B. This is going to be equal to rho 2 u2 a2. Okay. So the flow is steady. So there's no variability, there's no debility of that of rho. And now we're also saying that rho is constant to make it easy. Okay? And if density is constant, then rho 1 is equal to rho 2. And you're left to this.
Yes.
Okay? And because in this case A1 is larger than A2, so A1 is larger than A2, this means that U2 has to be larger than A1 in order to conserve mass. Okay? So the rate of change in time of density is equal to 0 because the fluid is steady. And I have some mass in and some mass out, given by the divergence of this. Okay. Let's suppose that density is constant along the streamline. Okay, nothing happens along the streamline during in the stream tube, which is a good approximation. So if rho 1 is equal to rho 2, then U1 A1 must be equal to U2 A2. So this means that in this case A1 is much larger than A2, so that U2 is larger than A1. So conservation of mass. If you have ever watered your garden with a hose or something, okay, you probably have noticed that if you squeeze the hose, the water comes out faster. Okay, so A1 at the beginning of the hose is the same. You squeeze A2 in order to make it smaller, and in order to conserve mass, the flow is steady, so the velocity at which the water comes from the pipe is the same. The density of the water within the pipe doesn't change. So in order to conserve mass, what happens is that the velocity at which the water comes out of the hose is larger than the initial velocity. Okay. That's the simple principle of conservation of mass for a steady flow. Now we can do the conservation of mass in integral form, which is much nicer. And we're going to take a volume V, whatever, okay, with a bounding area A, which is bounding this volume V. And the mass within this volume is rho dV. And we have a velocity and some dA. Okay, so there's some influx or outflux of mass on the bounding surface of this volume. So we want to look at the rate of change of mass within this volume, this big potato. Okay. So in this case, it's an outflow, and the outflow is going to be rho UdA. Okay, so how much mass is going out of the volume of which I'm integrating at some velocity u, integrated over the surface A that is bounded in the volume. If you integrate, so the whole outflow and outflux is obviously going to be this integrated over the whole area. Okay, the total outflow and inflow. So, rate of mass flow of the volume in the surface integral. So, it's going to be conservation of mass, okay? And so conservation, what does it say? So the increase of mass within the volume, or decrease, but let's say the increase of mass within the fixed volume, okay, this is not changing, so remember the Leibniz theorem, the limits of integration are not changing. So the increase of mass within the fixed volume increase of mass is going to be equal to the flux through the boundary. Okay, so how much flux is getting into the volume through the boundary? That is going to give me an increase of mass. A decrease of mass is going to be equal to the flux through the boundary negative. So d by dt of rho dv is going to be the influx, so because this is directed upward, is a minus rho uda. Okay. So mass integrated over the volume is going to change in time if I have some influx through the boundary. And as I have defined, dA is a minus for the influx.
Sorry, please, could you just repeat what you said for the last part again?
So, conservation of mass says that if there is an increase of mass within the volume of fluid, that is due to an influx of mass through the boundary. Okay? So, if mass is increasing in this room, it's because there is an influx of mass through the boundary, the surface bounding the volume A. So, as I have defined dA as outward and U out, so if there is an increase of mass within the volume, that's because I have, and the total outflow is equal to the surface integral of rho uda.
So the integral will be negative, obviously.
In this case, yes, inflow will be negative. Okay. So if you remember Leibniz, I'm not going to write this down again. Well, yes, because I have to show you this. So I have my d by dt of f over a volume. That is equal to df by dt integrated over the volume plus the area integral of the flux through the boundary. Okay, that was Leibniz in the general form. So what is this? Is this, okay, the rate of change of, in this case, mass, which is equal to this. So I'm going to write it. This change of mass plus the area integral of mass dA. For a fixed volume, of course, this is equal to 0. Okay, so the big potato over which I'm integrating is not moving, so that term is equal to 0. So the d by dt of rho integrated over the volume is equal to Now we're going to use Gauss to go from area integral to volume integral. Okay, so the right hand side is rho u a, and through Gauss, what do I get? Gauss relates an area integral to a volume integral. And so if this is my f, rho u, Right? So I went from an area integral to a volume integral. So now this is equal to minus rho u dv. So now I can put them on the same side. d rho by dt dv plus the divergence of rho u. Is equal to 0. Right?
Sir,
Yes?
so after that, we are going to treat material volume, or is it only for fixed volume?
No, we're just doing for fixed volume.
Oh,
Otherwise, you have to add some other tabs.
But
This,
are you using subscript for UA?
okay, I didn't use it before. U, whatever. And you could be, so in a material there would be, because in the notes instead of doing U, so for the material I wrote UF, U of the fluid, right? And in my notes I had UA, advection of the fluid. So just forget the subscript. It's not U and it's not UA or UF, it's just not moving, it's a fixed volume. So this term vanishes. So you're just left with this. Okay, so conservation of mass says that if you have an increase of mass within your volume integration, it's because there is an influx of mass through the boundary. So, well, I deleted it. So you look at Leibniz, just this, for a fixed volume, it reduces to this. And the rate of change of the mass with integrated over the volume is given by the influx of mass through the surface. Okay. So these two are equal. And so this is equal to the rate of change of mass within the volume. So now I change this area integral to a volume integral. And so the volume integral of the d by dt of density is equal to this. So now I have two volume integrals, and I can put them together. Okay. So the volume integral of d by dt of rho plus the divergence of the advective term. This is true for every volume. So d rho by dt plus is equal to 0, which is, again, the continuity equation. So this is the divergence term that we obtain by going from an area integral to a volume integral through Gauss. Okay. So the divergence term, we can write it in tensor notation like this. Okay, that's the divergence term, and I can split it into this. These two terms. So the continuity equation is now this plus this term plus this term of the divergence. Okay? I'm just rewriting the continuity equation by splitting the divergence term into these two terms. And this is Very good. So I can write the continuity equation as the Lagrangian derivative. Or and this is the expression that I used when I defined the string function. Do you remember that you said why there's a minus? So when we were looking at the string function, it was 1 over rho d rho by dt equal this. Remember? So if we put this on the other side, then the minus goes away. So that's how I use the continuity equation. And this was something like that.
String rate.
Yeah. Okay. Things are getting together. No? They should. That's the plan. To introduce things and suddenly say, oh, I've seen that already. Okay, I know where it comes from. So this is the continuity equation using the Lagrangian derivative. So this is the rate of change of density following a fluid particle, because the Lagrangian derivative is a Lagrangian description of fluids, of the movement of fluid. So liquids are almost incompressible, right? I made it. Liquids are almost incompressible, and density and changes in density are small. They're not zero, but they're small. Okay. So in the Boussinesq approximation, so liquids are almost incompressible, so changes in density are very small. So derivatives of density are very small. So for an incompressible fluid, all this d by dt, d by dx, d by dy, d by dz are equal to 0. And so for an incompressible fluid, I get this. So the continuity equation reduces to the divergence of the fluid for an incompressible fluid. Because this term vanishes. Okay, it's not 0, but it's very small. So the derivatives of this are going to be very, very small. Yeah? I'm not just saying that the flow is steady, I'm saying that the fluid is incompressible. So variations in density.
Yes.
No question. So I'm not just saying that the fluid is steady, so that d by dt is equal to 0. I'm saying that the fluid is incompressible, so variations in density are very small. So all the derivatives of density are going to be negligible. So the continuity equation reduces to this.
So compressible and incompressible.
Incompressible. So under the Boussinesq approximation that we did before, then variations in density are very small compared to the mean. So all the derivatives of density are going to be very small. So do I have time? Yes, I have time. Quickly. If you have any questions, please tell me now. No? So we could look at the conservation for a substance and conservation of a substance. Okay. And so we're going to consider diffusivity. Okay, so we look at some tracer, and this tracer can be diffused. Okay. And we're going to look at it at a molecular level. So to visualize where the diffusivity coefficient comes from.
I say visibility.
Sorry? Sorry?
I don't hear what you said. I
From the beginning?
Visibility.
From the very beginning.
Just like that.
Diffusivity. Diffusivity. Okay? We're going to look at diffusivity. Diffusion. So we'll get to the advection diffusion equation. So a tracer can be advected and it can be diffused. Okay? So if you throw some milk in your coffee, it can be advected if the coffee is moving, and the milk can be diffused in the coffee. Okay? So let's say this is my concentration, some some substance with some concentration C, and this is space. Okay, so it starts with some concentration C1 in space x1, and because of diffusivity, you might go to some concentration 2 at space x2. Okay, and it does so at some UC, which is a characteristic velocity of the molecular movement. Okay, molecules are moving all the time and they diffuse a substance, and they do it over a certain length L, which is called the free molecular distance. Okay, so diffusion at the molecular level, molecules are moving at some characteristic velocity uc, and they are doing it over a certain distance, which is the free molecular distance. Okay, so at the molecular level you can get diffusion, and so you might diffuse a substance from concentration 1 to concentration 2 at the molecular level. So the change in C is going to be given to uc times L, so the characteristic velocity times the free molecular distance, and the change in the concentration in dx. And this we're going to call it K dc dx, where K is uc over L. So this is meter per second, meter squared per second. These are the units of diffusivity. And this is the molecular coefficient, diffusion coefficient. Yes? Ask me.
UCL, DC dx or DL dx?
UCL, DC, dx, yes.
And then to the right is DC dx again.
Yes, so I'm just changing UCL to a coefficient K, and K is UCL. So what is the diffusion coefficient? Is given by the characteristic velocity times the free molecular distance. This is the diffusion coefficient of a particular, in this case, fluid at the molecular level.
Okay.
So the concentration, so the concentration will change in space multiplied by some molecular coefficient. Okay? If it's large, then the change will be very large. The diffusion will be very large. Okay? So the change in concentration due just to molecular diffusion per unit time. You look at the concentration, you integrate over a volume, and you look at the rate of change just due to diffusion in volume. This is going to be grad C. Okay, so the molecular diffusion in X, in Y, and in Z. So the change of the concentration over a certain volume, the rate of change or concentration of a certain volume just because of molecular diffusion, so there is no flow, there's no air coming through the window and out of the window. So there is some diffusion in this room. And so how does the concentration changes? That's due to the molecular diffusion. Okay, grad C. So the changes in X, in Y, and in Z, with no advection, with no flow. But the total change, and you're going to do this by yourself. So the total change in the concentration is going to be given by advection. So I might bring some concentration in through the window, and then there might be some diffusion within the room. Okay. So before we said that there is a mass in and mass out, and nothing happens within the volume of integration. Now there is diffusion within the volume of integration. Okay. So something might be happening inside the room. You have molecular diffusion. Okay. So the total rate of change of the concentration C will be given by advective processes and diffusion processes. So basically you have to put together what we did before plus an advection. So you can do again the advection of the concentration instead of density. You do the advection of concentration and you add, and you do the same for diffusion in X, in Y, and in Z. And you will end up to this. This is the advection term. And the diffusion term. Okay. I'm not going to do it because I don't have time, but it's just repeating what we did before. Okay. You.
Square.
Sorry.
We are taking grad square. That is Laplacian.
This is the Laplacian. Yes. How? You're gonna do it at home.
Oh, okay.
You're gonna do it at home because how? See, you're getting spoiled. I do everything for you. So you have advection in and advection out, as we did before for the advection. Okay, and in this, so if you do in minus out, what was the result? Minus d by dx of density dy dz, right? And you do that for the advection.
Okay.
And then you do that for diffusion. You do minus d by dx of what? dc by dx, not density. dc, you have dc by dx. dx, dy, blah, blah. And so what do you get here? If you do it in x and y and z, you get the Laplacian. Okay, and you have a k here. Okay, you have a k there. Then you make the assumption that the coefficient is a constant. So k can get out of the Laplacian for a constant coefficient. So this is the mass conservation for a substance which is subject to advection and diffusion. Okay. This was one of the exam questions, so do it. So derive the conservation for a substance. You have to do the advection term, and then you have, so whatever we did before, and then you have to do this in and out, and so you get the Laplacian for a constant kappa, for a constant coefficient diffusion. Okay, it's just, it's very simple. If you have any questions, please stop me. Ask now.
Okay. Sorry.
Class is over.
You just called the name of what you did. Is the conservation of
What?
that box? What's the name of the equation?
What is this?
Yes, the
Mass conservation for a substance.
okay.
I think it's in the slide as well. So you have the mass conservation for a substance. Now, if diffusion is equal, if there is no diffusion, so kappa is equal to 0, you recover the conservation of mass, the continuity equation, okay, obviously. So this is also a sanity check that you did things properly. If the conservation for a substance, you remove diffusion, then you're left with the continuity equation as before, okay? In incompressible flows, so under the Boussinesq approximation, density doesn't vary much, so this is equal to 0. So we were left with this, so the divergence of the flow is equal to 0. Right? And so if the divergence of the flow is equal to 0, this is equal to 0. This is the advection diffusion equation for an incompressible fluid. And I'm not going to write it down because it's in the slides. Okay? Diffusion is equal to 0, you recover continuity. For an incompressible fluid, it's divergent free, so this term is equal to 0, so you have the advection diffusion equation. And if advection is equal to 0, the Lagrangian derivative reduces to advection is equal to 0, so there's no air coming in and out of from the window, so advection is equal to 0. So this is what? How do you go from? So if u is equal to 0, there is no advection.
Advection is just a single time change.
So the change in the concentration is just given by the diffusive processes. So this is the diffusion equation. The one below, the one above is the advection diffusion equation, and the one below is the diffusion equation. So the room is closed. There's no advection of concentration in and out. Whatever happens to the concentration within this room is just given by diffusive processes. Okay, so here in the slides you have whatever we did at the beginning, the starting point, okay, with the rho u1 on one side is equal to rho u1 plus whatever happens in delta x, and we reach the conservation of mass, or you can write it with the Lagrangian derivative. For a steady flow, it reduces to equation number 3, and for an incompressible flow, it reduces to divergent free. This is obvious application of continuity. And then conservation law for a substance or a tracer. You got a molecular coefficient which is equal to U times L. That's why the unit is meters squared per seconds. Okay. And so what you have to do in order to reach this is that the total rate of change of the concentration is advection in minus advection out, so what we did on the board before, plus diffusion in, diffusion out. So diffusion in, diffusion out. If you have some d by dx of this, then you get the Laplacian. Okay? So one plus the other. So you get the advection term and the diffusive term. Yes, that one. So for incompressible fluids, that's equal to 0. And so you get the advection diffusion equation, this one, equation number 9. And if you assume no advection, then u is equal to 0, and you just have the diffusion equation.